Tyrosine is one of the 20 amino acids that's used to make a protein within the human body. Just like every other amino acid, tyrosine has a center carbon, central carbon, alpha carbon, chiral carbon, stereocenter carbon, the carbon that's got 4 different attachments to it. One of those attachments is a carboxylic acid group where you've got a carbon with 2 oxygens, one of those oxygens being attached to a hydrogen. It's also going to have an amino group where you've got a nitrogen and 3 hydrogens attached directly to this carbon. This nitrogen should only have 3 total attachments, so the fact that it has an extra hydrogen attached to it means that this is going to carry a +1 charge. Then it's also going to have directly attached to it a hydrogen, and then the thing that makes every amino acid unique and different is the R group that's attached to the chiral carbon. At its lowest pH, the environment is going to have a whole lot of extra hydrogens around, and so all of the places that this molecule can have a hydrogen is going to happen. So at the lowest pH possible, the fully protonated form of tyrosine is going to predominate. As you increase the pH, or as the system loses some hydrogen and this molecule is going to start to have more hydrogen than the system does, the molecule is going to have to give up some of its hydrogen to the system to balance things out. The first hydrogen that gets lost into the system is from this carboxylic acid group. This oxygen is going to lose its hydrogen, gain back its lone pair of electrons, and now this oxygen is going to be negatively charged. That's going to happen at a pH of about 2.2. At this point, this nitrogen is still positively charged, and so we've got this -1 and this +1. Those are going to balance out to 0. So overall, this molecule is going to have a 0 charge. But because there are actual places where there are formal charges on this, it's not just going to be a neutral molecule. This is going to be called a zwitterion. And as you increase the pH, go up, the final hydrogen is going to be lost from this nitrogen at a pH of about 9.2. That nitrogen is going to lose its hydrogen and gain back its lone pair, and now this nitrogen is going to be neutrally charged. This oxygen is still going to carry this -1 charge, and so this neutral and this -1, overall this molecule is going to carry a charge of -1, but that's only going to happen at pHs over 9.2. In the human body, or at physiologic pH, which is a pH of about 7.4, this nitrogen is not going to have lost its hydrogen yet. It's still going to be attached. So the zwitterionic form, or the neutral form, where you've got a negative and a positive on the same molecule, this is the form that's going to predominate for tyrosine within the human body. Now let's talk about the R group. So as you can see, there's a huge aromatic ring where you've got 3 double bonds as well as 3 single bonds. These double bonds can move position and that increases stability. So this is considered an aromatic ring. All of these are nonpolar bonds, but you've got this OH group here, and this OH group isn't somewhere in the middle of it. It's off to the side. This is pretty easily accessible. So this oxygen is creating polar bonds with this carbon and this hydrogen here, and it's able to use advantage of the fact that it has polar bonds to do hydrogen bonding with other molecules. This is considered polar because of this alcohol or this OH group attached to this aromatic ring. This part of the ring is called a phenol group, and then you've got an alcohol. So this is always ends in OL, so you've got a phenol. So this overall R group is referred to as a phenol. Now, although this ring is pretty bulky, this ring can come from other molecules. So tyrosine is not an essential amino acid. You don't need to eat it for it to show up in the human body. However, if you don't eat enough phenylalanine, your body's never making tyrosine. And so at that point, this does become an essential amino acid. Another way in which tyrosine can become essential is if the enzyme that's used to convert from phenylalanine to tyrosine isn't functioning correctly. Then you're never going to be able to make tyrosine, so you're going to have to end up eating it. So in normal, healthy individuals where nothing's going wrong and phenylalanine is able to be converted effectively, tyrosine is not an essential amino acid. If that process isn't happening correctly, tyrosine does become essential. One of the really important things about tyrosine, this OH group can get removed and a phosphate group can get added to it, and that is called phosphorylation. Anytime you phosphorylate something, the enzyme that you use is called a kinase. And so if you're phosphorylating tyrosine, The enzyme that's used to phosphorylate tyrosine is going to be called a tyrosine kinase. And tyrosine kinases are one of the most important enzymes involved in intracellular signaling.